A murder has occurred. Oh no. The body has been found in the park, which has an ambient temperature of 17 degrees Celsius. The body was discovered at 10 a.m. with a temperature of 22 degrees Celsius. An hour later, the temperature of the body was measured as 19.5 degrees Celsius. Using Newton's law of cooling, come up with a function in terms of time to model the body's temperature, and assuming a natural human body temperature of 37 degrees Celsius just before death, deduce when the murder took place. Okay. So I like a question like this because it's not your average Newton's law of cooling question. Usually it's like a teacup, a cup of tea, cooling down, or a popsicle warming up. But this one's nice. It's a little actiony, but it's also something that actually does happen. Okay? You can use Newton's law of cooling a little more complexly than what we're doing here, because I doubt very much parks throughout the day stay the same temperature. But you can use Newton's law of cooling to help try and figure out when a body was killed. There are other things you can tell, other decays from a body that can help place the time of death. And this is something that's actually done in forensics. So I like that one. Okay? Or I like this one, I guess. I like the concept. Anyway, so what are we going to do? Well, they tell us right away, use Newton's law of cooling. So let's remember, what is Newton's law of cooling? So if we've got theta, we'll use capital theta. You don't have to. Okay, you could use capital T to represent the body's temperature, but theta is used more in science for temperature, but also we're going to have T for time, and I don't want to be confusing and say, oh, look at T. Does he mean time or does he mean temperature? So we'll do theta of T is, we'll say, the body's temperature. We'll say, so we could do one of two things. We could say at time T after the murder, or we can say after, what is it? We only mentioned hours in the question. Yeah, it's 1 hour later. So we'll measure in terms of hours. Okay. So after T hours, and you can either measure from the murder, or, this is what I'm going to do, you can measure from when the body was found. Okay. We'll get a slightly different function either way, but you'll still get the same end result. We'll still be able to calculate the correct time of death. Okay. It's just a question of, at the end, are you going to try and solve for theta at 0 or something else? I'm going to say from discovery. Okay. We'll see how that goes. And I would encourage you to try it the other way. Try calculating T hours after the murder. But you'll still be able to do it. I want to do it this way. Okay? The reason I'm picking it this way is because the information I'm given can translate very quickly. Okay, so 10 a.m., that would be time 0. An hour later, time 1. Whereas if I don't know when the murder occurred, is this going to be T 2 hours after the murder? Is this going to be T 3 hours after the murder? If I don't know when the murder is, how do I know what T values I'm working with? Okay. So that's what I would probably do. But you can get away with that without doing that. It's just more complicated. And why make our lives more complicated? Okay. So there's the body's temperature, and what are we trying to do? Well, we're using Newton's law of cooling, which says that the change in temperature is proportional to the difference between the temperature and its surroundings, what we call the ambient temperature. Now we're told in the question the ambient temperature of the park is 17 degrees Celsius. Okay, I'm going to drop the of T and just use the capital theta here. Okay. And what we've got is a nice differential equation, a Newton's law of cooling differential equation. And we can solve this a couple different ways. You can expand it out, treat it as though it's linear. I'm going to treat this as a separable differential equation. Okay, so we'll bring the dt over to the other side. I've got k, a constant, but I can treat that as though it's a constant function of time. And then over here we've got our function in our variable theta. Okay, so we'll bring over the theta minus 17 here. We'll keep the k over here, and we've rearranged. Now it's time for us to integrate. That's the next step in solving a separable differential equation. Okay. So notice over here we've got, on the left, theta minus 17 d theta. Okay. Now, the derivative of theta minus 17 with respect to theta is just 1. Okay, this is a classic situation where we can replace this with ln. So integrating this, we just get ln. Okay. And then over on the other side, what have we got? K dt, kt plus a constant. Okay, so we're going to come along, take both sides and raise them as powers of e. So e to the right-hand side, e to the left-hand side. Okay, we'll be left with theta minus 17 is equal to e to the kt plus c. You can let the e and the c sort of absorb together and become a much bigger constant, multiplied off on the side there. And we'll bring the 17 over. So 17 plus c e to the kt. Okay, so that's our function in terms of time for the temperature of the body after it has been discovered. Okay. But we have an incomplete picture. I've got some constants, k and c. I need to find them. I need to solve for them. Okay, and then we can figure out the murder time is the time where this expression is equal to 37. Okay. But in order to try and use some algebra to solve for t, we first need to know what c and k are. Alright, so what are we told? Well, since we're measuring from when the body was discovered, times 0, 10 a.m. in the question, has the body's temperature at, what was it, 22? 22 degrees, yes. Okay, so 22. So that's 17 plus c e to the k times 0. And we can quickly see that c is going to be 5. Then, 1 hour later, and we know that the body's temperature was 19.5 degrees Celsius. So that's 17 plus, instead of c, we'll write 5. E to the k times 1, which is just e to the k. Subtract 17 from both sides. Divide by 5, you'll get 1/2 is equal to e to the k. So that tells me k is going to be ln 1/2. Or you can write it as minus ln 2. That's fine, that works. Okay. So, what do we do now? Well, this has given me c and k, so now I really do have my body temperature function, or maybe corpse temperature function. Okay, so k is ln 1/2. There we go. There's our temperature. We've got the function that we want, but what do we do now? Well, if we were to do something like, say, let Tm be the murder time. Okay. So that's the time in hours relative to 10 a.m. when the murder took place. We are told in the question we are assuming a body temperature of 37 degrees. So we know 37 should be the temperature at the murder time. So subtract 17 from both sides. Divide by 5. What can we do here? Well, we could, I guess, apply ln to both sides. So ln 4 is going to be ln of e to the ln 1/2 Tm, except the e and the ln cancel out. So we're left with ln 1/2 times Tm is equal to ln 4. Now 1/2 and 4, I notice both of these are powers of 2. So we can rewrite everything in terms of ln 2. Divide by ln 2 on both sides. So 2 is equal to negative Tm. Or Tm is minus 2. So, okay, great, but what's the interpretation here? Well, 10 a.m. is 0 hours into our investigation, or 0 hours into the study of the body, 0 hours into the discovery. Okay. Minus 2 would mean 2 hours before, because we're measuring T, and we even said this a while ago, T after T hours. So after minus 2 hours, well, that's the same as saying 2 hours before. Okay. So strike that, we'll say murder is 2 hours before. Because no one says minus 2 hours after, although that's what it means, is 2 hours before is minus 2 hours after. Anyway, so if the murder took place, or if the body was discovered at 10 a.m., 2 hours before, we can say the murder occurred at 8 a.m.